Yeah, so let's do this. Okay, so for the quiz, I want you guys focused on the Diels-Alder and the sort of Cope-Claisen. So maybe what I will do. All right, let's do this. There's going to be 4 questions. 4 questions. So ignore my syllabus and what the quiz said. It's tentative anyway. 4 questions. 2 Diels-Alder questions, right? Where I'll give you a Diels-Alder reaction, right? You have to sort of, you have to be able to draw the Diels-Alder product, right? You have to be able to understand what the regiochemistry of it is, and you have to be able to draw the stereochemistry. And the second, then the third and fourth questions will be on sort of Cope/Claisen. Sort of same thing. You have to sort of, you're given the reaction. In that case, you're going to sort of want to predict the stereochemistry. So that's going to be kind of what you're going to need to know. And what we're going to do today is we're going to spend the whole day today sort of refreshing on that. And so we'll treat this maybe as a little bit more of a recitation-esque type class, and we'll go over Diels-Alder reactions, and then we'll go over some Cope and Claisen. So maybe the first half we'll do Diels-Alder type recitation, second half we'll do Cope-Claisen. And then on Wednesday, I have to look and see if we can get through all of amines in Wednesday, but that won't be the quiz. So don't worry about the amines for the quiz, because I know that this is a tough part, and I'd like you guys to focus on trying to get this stuff down, okay? So I left off, before we get into that sort of recitation-esque, I did print out a paper because I left off last week sort of pointing out that Cope and Claisen rearrangements, right, one of the things that you might want to consider, and this type of question come up on an exam, is kind of, here's an equilibrium of a Cope, here's an equilibrium of a Claisen, and sort of, which way does that equilibrium lie? And sort of within Claisens, right, we sort of describe how Claisens, just gotta make sure I have it right. So for the Claisen, right, one of the things that we left off with last week was how Claisen rearrangements, right, unlike Cope's, Claisen rearrangements can oftentimes, or are generally, what we consider sort of irreversible, right? So the Cope, you could draw Cope where the starting material and the product are the same thing, right? So the Cope is just a 1/6, right? So the Cope is just, and I'll erase this in a second. But so the Cope, by its very nature, in this case, we're literally drawing the same molecule on both sides. And the idea with the Cope is you begin to put substitution on that, substitution over on these two becomes these two, substitution here becomes there, and there's stereochemistry associated with that, right? But the sort of equilibrium, right, is going to favor based upon that substitution. Which way the equilibrium is going to lie is going to be based upon that substitution. So things like, more substituted double bonds, right, are something that came up a lot, right? If you have a di or tri-substituted double bond versus a terminal substituted double bond, well, it may favor the more substituted double bond for reasons that we sort of know. And I asked you guys to just have a sort of a thought experiment. This is a Claisen. If you want to go in the reverse, right, that would become a retro Claisen. And I just sort of wanted you guys to think, just plant in the back of your head to start to sort of realize that on this basics, core here, this goes in this direction. Why, first of all, really quickly, why does the Claisen favor this side, this direction?
C double bond O is more stable than that double bond.
Yeah, so the carbonyl, the stability of the carbonyl is something that we've seen a lot, right? The enol keto tautomer, right, we generally favor the keto form. Anybody have any thoughts about how we might drive a retroclazen? What are some of the things we might do to stabilize or sort of drive a retroclazen? Any thoughts? Based upon some of the things that we've seen?
You could just move those pi bonds around and kind of like move sigma bond because it's like due to like homo and lumo, I'm guessing.
Well, it's the same arrows.
Yeah.
I mean, the question isn't how do we push the arrows, right? Pushing the arrows is the same thing, just, it's just in the reverse. The question was more a question of thermodynamics, right? It's an energetically, in the case of the Cope rearrangement and the Claisen, right? They're reversible, right? And so the reaction is inherently thermodynamically driven. In the case of the Cope, it's going to be depending upon the substitution because at its core, it's all carbons. But in the case of the Claisen, right, it goes this way because a carbonyl is energetically more stable than an enol ether. Right? The question sort of was, well, we can do it in the reverse. What can we do? And I don't mean take this reaction and make it go this direction. I mean more like, can we put substitution on this to make it go, for example, in this direction? Yeah, Mike.
Could you use a catalyst like we used in the aromatic substitutions?
Catalysts lower energetics of transition states, right? A catalyst is going to lower the transition state barrier, generally, right? It's going to be very difficult. I mean, I'm not saying impossible, but I think to get a catalyst to overcome thermodynamic control is a pretty advanced concept, right? Because really all that you're doing for catalysts is you're generally lowering the transition barrier, right? You'd almost have to lower one selectively over the other in some way to do that. But so it's not that it can't be done, but that's maybe a little bit more complex than what I'm looking for here. Yeah?
Another idea, reducing this molecule to alcohol.
Well, if you reduce it to the alcohol, right, if anything, that's going to push it in this direction further because you're going to render this irreversible. Right? Yeah.
What if you add like a very strong withdrawing group next to the carbon?
That's one of them. Yeah, so that was one of my thoughts, right? So if you guys recall, what makes a carbonyl, so carbonyls are generally much more stable than enol ethers. That's one area we saw. We also saw it with hydrates, right? We saw that in general, if you have like, acetaldehyde, right? If you guys recall, the hydrate, right? If you guys recall, the hydrate, if you sort of say plus water, right? This sort of equilibrium of the hydrate, this is another example, right? The hydrate is not stable, right? For all intents and purposes. However, we did show one example of where the hydrate is energetically favored. Formaldehyde, no. Formaldehyde forms like a trimeric form or a polymeric form. But you said it. What did you say? You said an electron withdrawing group, right? And that's in fact what you can do. In fact, if you put 3 chlorides here, right? This is actually a Mickey thin. It's like basically can actually drive the other direction. And what you're doing here is by adding electron withdrawing groups, what do you think that you're doing? How does this affect the equilibrium? Based upon some of the things that we've seen in the past. Yes, but why? How does the electron withdrawing group have that effect?
It makes it more unstable because there's a partial positive.
Right. So by putting those here, the question becomes, the way to think about it is, okay, well, if it's shifting it in this direction, it's either going to stabilize this side or destabilize this side. And the argument is that it's destabilizing this side, right, because the carbonyl, right, has this dipole where you have a delta plus there, and now you've got even more electron withdrawing groups on there. So yeah, so one of the things that we could do is, for example, maybe if we put, I don't know, what do you think, maybe 2 fluorides? I have no idea if this would work or not, but I would imagine it probably would, right? Maybe you put 2 fluorides there, and then you end up with, I'm going to look to see if this is actually known or not. I would imagine that it probably is. But certainly, whether it's not known or not, it's certainly a rational thought process behind how we could shift the equilibrium in that way. So electronics would be maybe one way that we could get it to go that opposite direction. That was one thing that I was thinking that you guys might be able to come up with. And there's one other thought that I thought maybe you guys might come up with. Right? What we're doing, right, in this case is we're destabilizing the carbonyl based upon electron withdrawing. Is there another way that we could destabilize this structure which wouldn't necessarily be as destabilized over there? And actually just printed out a paper on this to sort of show you guys. But another thing that you can sometimes do is you could add strain, right? Like imagine a scenario where you had, say for example, a 4-membered ring there, right? What's going to happen when you do the cope?
It'll open up.
Yeah, it'll open up. And so I'm going to double check the stereochemistry here, because there's probably going to be some stereochemistry involved. But certainly you can imagine a scenario where you have ring strain, right? And by doing that ring opening, I don't think it's this, I think it's, same idea, but basically it's not the trans double bonds, it's the cis double bonds, right? It's a little bit more stable. And I printed out a paper that actually did this, that I thought was kind of neat. But I think I'm not going to discuss it. But basically, this strategy has also been done. There was a paper I was going to talk about, but looking at the time, I think I'm going to save you guys this, but maybe I'll come back to this on an exam or something. But anyways, this is something that you can clearly see. It's also a little bit complicated, right? Because, we're going from one ring structure to another ring structure, and sometimes that can be complicated, but that's another example. So the idea here, the point to what I'm trying to get across to you guys here is the sort of recognition that these reactions are reversible, and then that reversibility will ultimately lead to products that would be driven by thermodynamic control. And that even in a situation, say for example, like a Claisen, right, where we always think about a Claisen going this direction to that direction, right, there are things that you can do to actually push it in the reverse direction. And certainly I'm sure that as soon as people started thinking about the Claisen reaction and they realized that it was reversible, people started to think of, well, what are some ways that we can make that go the other way? And this is one of the ways that you could do that, just by thinking about that thermodynamic control. Okay? That's all that I wanted to sort of get at for this part. Okay, and this sort of furthermore, I think, sort of emphasizes a point that I've been trying to make throughout this semester and even last semester, and that's all chemical reactions are, at least in principle, reversible. Okay. All right, so let's do some problem solving. Okay, so we'll start with Diels-Alder. Okay, I'll throw up an example of a Diels-Alder, and I'll give you guys a few minutes to try to solve this on your own. Those that did the recitation, I think I'm going to go through a similar thing that I did with the recitation, which is a sort of a 3-part system here. So I'm going to show a diene and a dienophile, and I'm going to break this down into individual parts to sort of walk you guys through it, and in terms of like stepping up different levels of knowledge, right? So let's start with let's start with this. Okay, so I'm going to put a methyl group here, and I'm going to put a methyl group there. Okay, so that's going to be my diene. Okay, it's electronically rich. And what I'm going to do is I'm going to have that react with a little bit more complicated Diels-Alder product than perhaps we're used to seeing, which is that aldehyde. Okay? And so what I want you guys to do for starters is I'm going to break this down into steps. Now, if the question is simply asked to show the product on an exam or whatever, you're not going to have to go through all these individual steps, but I'm going to go through this as a way to sort of build up skill level, right? Like the first thing that you need to be able to do is show me a Diels-Alder product, right? And there should be, for any Diels-Alder product, right, there's two regioisomers. So the first question that I want you guys to answer is, show me the two potential regioisomers. Or both hypothetical regioisomers. Don't worry about stereochemistry at this point. So don't show any stereochemistry, just draw both regioisomers. Okay, so that's going to be step one. Once you draw both of those, the second one will be choose which of those two. Step three will be based upon the regioisomer that you choose. Show all stereoisomers, hypothetically. And then number four, choose correct stereoisomer. Okay? And so the way that I would sort of, I don't take this literally. I'm just going to sort of use this as a sort of just so you guys sort of understand where I'm going with it. Show me any Diels-Alder product. I don't mean this by heart. I'm just going to say it. Show me if you can show me both Diels-Alder reactions, you get a C, right? If you can choose which one is correct, you get the B. If you can then choose the right stereoisomer, there's your A. So that just sort of gives you a guideline of how you start at the beginning, make sure that you can do that, and then build your skill level to one where you can then choose the regioisomer. Because you need to be able to do this before you can do this. You need to be able to do this before you can do this, right? So this is kind of minimal knowledge that I want you guys to obtain, knowledge to pass with flying colors, to pass with distinction, okay? And I'll give you guys about 3 minutes. And if you have any questions, in about 3 minutes we'll discuss the two regioisomers. Okay, then I'll give you guys a little bit of that. I haven't thought through it. Well, so you have to choose one of those two regioisomers.
Yeah, because basically in this case, both tolerate next to each other, and this is facing inward. And in this case, it's the same thing, but just upside down.
Wait, is this and this just the same thing? What the? Well, this and this are the same thing. So
But the products both have the same.
you don't have to do all four.
So
You did 4, but 2 of these are going to be the same. Just hold one the same, and then just move the other two. Does that make sense? You did all 4.
So then that would be
You sort of, I guess, actually no, you showed 4 because you were then showing the endoenzo of each one. I was more showing it as more like a funnel, right? I was funneling down,
Okay.
right? So you went right to the 4. I'm saying, basically, start with the 2 regioisomers, then take the diastereomer that results from that one regioisomer. Yeah.
take 2 regioisomers.
So what does it mean when I'm saying regioisomer?
where the groups are
Yeah, so it's sort of, when we're saying the 2 regioisomers,
based on like the partial positive and partial negative.
right, so if you held this and you imagine that Diels-Alder, right, that would be one of the regioisomers. The other regioisomer would be if I held one the same and flipped the other one upside down, right? Or held this and flipped the other upside down. So those are your 2 regioisomers.
Yeah, I gotta see.
Right? Okay, well, you got to draw the products correctly. You got to make sure that you that you have the Diels-Alder product, right? It has to have, what does the Diels-Alder product lead to, at least in this case? What's the core? Right? You got to make sure that's correct. It's not just about the groups, it's about all the electrons and everything else that's in there as well.
There's supposed to be 2 or 4 stereoisomers.
There's more than we are used to, because usually there's endo and exo. I'm using this as an opportunity to explain something added that we didn't necessarily touch on. So technically there's a lot more stereoisomers that can result. At the end of the day, there really is only endo and exo, because by its nature, Diels-Alder chemistry, the concerted nature, basically means that certain stereochemistry is going to be set. And what I mean by that is, I'll explain that one. Okay, so now think about what the next one is. All right, so what's that? I just want you to draw the Diels-Alder products first. I just want, because I, when we're going through these, I think, sometimes people can be overwhelmed because they're trying to go from 0 to 100. I think I want you guys to just make sure that you can draw a Diels-Alder product first, right? Then once you are comfortable being able to draw the Diels-Alder product, then the next step is, well, let's draw the right one. And drawing the right one would be both drawing the right regiochemical outcome as well as the correct stereochemical outcome. And that's one of the reasons why the Diels-Alder reaction becomes one of the more challenging reactions for you guys to understand. Okay? All right, so right, so just as a quick reminder, again, the Diels-Alder reaction, right, is going to be this, right? We're basically trading 2 double bonds for 2 sigma bonds. So we're basically going through from a system where we have 3 pi bonds, right, to 1 pi bond and 2 sigma bonds, right? So the p orbitals, this became a sigma bond, this became a sigma bond, and then this one shifted over, right? So now we've got 2 additional sigma bonds, and we've retained one of the pi bonds that has come through the process, right? So as it's established, right, that should be your core. Now, I've asked some questions. One question that I loved on one of the old exams that I gave, which I'm not going to get into right now, but systems where you have, for example, alkynes instead of alkenes, and what that leads to, and that sort of takes getting through. But right now, we're just focused on typical Diels-Alder reaction. And as is drawn, right, if we sort of number our carbons, 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right? The 2 and the 3 are going to be the double bond. At carbon 1 is our methyl group. At carbon 2 is what?
OME.
The OME. Right? And then we have 5 and 6. We have to worry about 5 and 6, right? There's nothing at 3, but we have our bond between 2 and 3. We have our 3, we have our 4. What's at 5?
Methyl.
Is our methyl group. Again, we're not going to worry about stereochemistry right now. That's going to be next. Right? And then our aldehyde is going to be here. Okay? So this is one of the regioisomers. Okay? We have an additional regioisomer, right? Which would basically be if we flip this over, right? So that would mean that the aldehyde would be down at 5, and the methyl would be up at 6. So the regioisomer would simply be the same thing, but we just flip-flop the aldehyde. Now there's other ways that you could have drawn this that are also correct.
Can you flip both?
There are also, well, if you flip both, you'd have the same molecule.
But not in.
So there's multiple ways that you could draw this alternatively that would be correct. There's even more ways that you could draw it that would be wrong, right? But I simply kept when I was trying to draw the regioisomer, because the regioisomer is just this versus this, or this versus this, right? It's going to be the same thing, depending on how you do it. So if you flip this one over instead and made this 4 and that 1, you just get that flipped over. But just like anything, you sort of don't make life more difficult for yourself. Just hold one part the same and modify the other part. Okay? So these are two, unless I'm missing anything, these are the two potential Diels-Alder regioisomers that we can get. Okay? So you have to ask yourself, were you able to draw those? Hopefully you're able to draw those. Okay? So these are the two hypothetical regioisomers that you could get. I may even ask questions like this to sort of help distinguish different knowledge levels from one another. Okay? So if these are the two hypothetical Diels-Alder products, now the next part of this comes up, well, which one of these two, these are both hypothetical, which one of the two is going to be selected for? Right? And I've got, let me give you guys just a minute to think about it. So the next question is, which one of these is the major product? Seeing some people say the right, seeing some people say the left. Just think about it a little bit. How do we just to sort of go back to how we decide? How do we think about the regioisomers? Someone that hasn't. Someone else. Go ahead, Jimmy. What's that? Yeah, so we want to sort of figure out the partial charges, right? We're going to think about it in terms of electrostatic. And this we're going to see a lot. Systems like this, when you see an alpha-beta unsaturated ester of this type, you're going to see these a lot, right? And so, you know, you don't necessarily need to go through the process of drawing all the different, you know, charges and thinking about the partial charge. But when you see this, at this point, we've seen these types of alkenes quite a bit in the past, right? Where did we see these? We saw them in Michael additions, for example, right? And it's electrophilic at this carbon. And what that tells us is that this carbon is going to be the more electrophilic site on this. And that's going to be our delta plus, right? That's going to be the delta minus. We can also think about the fact that if you put a negative charge on that carbon, that's kind of like an enolate, right? So it's stabilized up through the enolate in that capacity, right? So that would be this guy. This one was a little bit more, I made this maybe a little bit more, I don't want to say ambiguous, but I made this one a little bit different to, I think, make an additional point, right? All right, so the question becomes delta minus versus delta positive, delta minus versus delta positive. Let's just start with one, and we'll just go with, say, for example, delta minus. How many people think that the delta minus is this carbon? See, Patrickson? Patrickson's hands up? How many people think that this carbon? See, a couple additional hands up. A lot more hands on that one. Patrickson, do you want to change your answer?
No, I'll go on with you.
Leanna's with you.
Because if you bring the electrons down and then you move...
Stand your ground. Yeah, no, Patrickson's right. So and this is why I wanted to sort of bring this up, because I thought that because we're dealing with really two different groups, and I wanted to sort of make this point. I expected quite a few people to maybe mix this one up, so I wanted to sort of go through this. Okay? Let me just start with this question to everybody. Here's just a fundamental question that sometimes people don't necessarily appreciate that much, and I have to drill it home, and here's a good time to drill it home. Which of those two carbocations is more stable?
The top one. The bottom.
I got about an equal amount of people saying top and bottom.
Top is aggressive.
How many people think the top? How many people think the bottom? Okay, so maybe not quite equal. But the people that said the bottom, why do you think the bottom? Michael?
You said last class that
Did I? I don't. That was not the answer I was expecting. But so maybe we'll try to clarify that because I'm not quite 100%. I was expecting some people to say something else. Yeah.
The reason that people would say the top is because oxygen's more electronegative, so it has.
Wait, hold on. No, we said which one's more stable.
I think the top one's more stable.
Okay, somebody that thinks the bottom. Eric, you had your hand up.
Yeah. Well, I was thinking there's more like free electrons around the oxygen. That kind of.
Wait, so now you're going for the top.
No. Well, the bottom's more stable, as in. Yeah, no, it's still the bottom's more stable. Yeah.
Why?
Tertiary carbon.
See, that's the answer I was expecting people to say. Right? So I think that the answer that people often see, and I think there's a lot of confusion with this, is that one of the early rules that people learn about carbocation stability is more carbons around the carbocation the better. Right? And the argument becomes hyperconjugation. Right? You have all of these carbons around, and tertiary carbocation we've learned is fantastic. But there's something better than hyperconjugation. Conjugation. Right? Resonance, right? And oxygen, even though oxygen, this can be a little bit confusing to people because it's a little bit counterintuitive, but people think about the oxygen as being electron withdrawing, right? Because it is. Oxygen's more electronegative. Except that oxygen is fantastic at stabilizing resonance forms because of why? What does that do for you? Even though we're putting a positive charge on an oxygen, and you might say, I don't want to put a positive charge on oxygen, that's electronegative. What's good about that? Say it louder. Octet, right? This is one of the things we always try to fill, right? Octet rule, you never want to break the octet rule, right? So never go beyond 5 bonds to carbon. But the octet rule is also valuable in terms of a stabilizing factor. If things can have full octets, that's really good. That explains the classic example of why this is the case is all these borons that we often talk about. Boron in its neutral state only has 6 electrons around it. So boron naturally doesn't exist in that neutral state. It'll exist as a negatively charged borate, the B-, so that it can have a full octet, right? So boron is a classic example of this. So yeah, so absolutely this one is more stable than this one. Yeah.
For the partial positive, can't those other pi bonds resonate up?
Well, let's. You're jumping ahead. Let's. So, are we clear here? Right. Tertiary carbocations are great, but if you can get that resonance stabilization, that's even better. Okay, that makes sense. Okay. So now let's consider, the two forms that we have, right? Put the positive on one, the negative on the other. Positive on one, negative on the other. Right.
Why is the bottom version positive?
Just give me a second. I'm thinking through this for a second. So basically what I did was I moved the electrons this way
And how does that make that positive?
for the other way. So if I did this, positive charge here, negative charge here. If I went the other way, negative charge here, positive charge here.
Didn't you say that the oxygen?
Hold on. So there could be other resonance forms here. These are the extreme examples, right? These are the two examples where we basically have a positive on one side and a negative on the other. And I think somebody's getting a little ahead and maybe seeing. I think the question that we want to ask here is of these two, and this is tough. There's a bit of gray area here, and I recognize that there are certain things here that might be a little bit confusing because these are in essence resonance forms from one another. And what we'll see is occasionally we have to look at additional resonance forms of these resonance forms to help us explain the answers. But of the two, I think that inherently, in our guts, just looking at the two, which one do you think is more stable? Yeah, I think inherently, if you guys were to just look at these, you'd immediately think the bottom. And I'm guessing that's why so many people chose the bottom one, right? Because it just looks that way. But you got to dig a little deeper into these two. Okay, Patrickson, where are you? I can't see you.
Yeah.
Why did you pick the top one? What is it about that top resonance form that you liked?
The ability for the double bond to kick off on the charge and create
I can't. Can you speak a little louder?
the ability for it to create that tertiary cation on the bond side.
Well, that would be the bottom.
Resonance.
Yeah, Nagora.
More substituted double bond on the top one.
Well, they're both the same substituted double bonds. Yeah. Okay. Go, Leanna.
Oh, can you just take the electrons from the oxygen,
Yeah.
bring it
And-
down, and then
Yeah. And so this is where it's a little bit maybe. It's like, wait, aren't these all resonance forms? So I get why this is a little bit, sometimes a little bit more difficult to see, right? But you can't necessarily do the same thing here. Do you guys see how that's sort of a nice little network within there, stabilizing that positive charge on that side of the group, where you basically have this group here. Another way that people sometimes do this and can be helpful is, so do you guys see that? I know it's like, well, we're showing all these resonances. Aren't they all resonance one another? But the fact that we kind of have this little additional stabilizing factor up onto that oxygen. Who had their, yeah.
So why can't we do the same as
You can't, you can't,
So they would create.
you break that Ket rule down there, right? You're sort of stabilizing
It would move the other way.
no.
here over here, not through resonance. That would be sort of through space. So I get that this one's a little bit tricky. I'm going to show you guys one alternative way to maybe look at this that sometimes is helpful for people. What is that group there that I just circled? What is that? Yeah, Patrickson. What's that? Well, yeah, technically. That's not what I was looking for, but you're correct. I was looking for something a little bit more about the reactivity of that group. What is that group? Yeah, but it's a specific type of alkene. It's a special alkene. Because it's got that oxygen on it. Yeah.
Is it a Michael?
Well, it's an enol.
Mhm.
It's an enol. And what do we know about enols?
Your reactor?
Enols are nucleophilic at that carbon. Why are they nucleophilic at that carbon? Because you can put that sort of negative charge there, right? By basically pushing electrons down there. And that would get you right to that one. So understandably, this is, I maybe put a little bit more of a challenging one up here because I wanted to sort of explain this to you guys a little bit. But that oxygen, if you have an oxygen in these systems, they can really help promote the regioselectivity wholeheartedly. Okay? Okay, so that means that this would be your delta minus, this would be your delta positive, right? Which would basically mean that the way that I have it set up is right or wrong? Wrong, right? I have to flip over the one side. So it's not going to be this one, but it's going to be that one. Okay? Okay. If you were confused a little bit about the sort of the methoxy versus the methyl group, it's understandable. So don't feel like, oh, I can't even get the B, right? That's not where I was going with this. I was just trying to sort of give it maybe a little bit more of a challenging question to sort of explain how, given the priority, similar to, you know, the donating nature of a methoxy group, for example, on a benzene, right? It's better than a methyl group in many ways, again, because of that resonance stabilization that the oxygen has. Okay. All right. So that's that one. We're running out of time already. Okay, so let's keep going then because it's already 10:15. Okay, so the next question becomes stereochemistry of that. Okay, And there's a lot of stereoisomers that you could have on this, except that there's one simplifying factor in this chemistry, right? And that's that when the Diels-Alder happens, the relationship between those two groups, what's the relationship between them?
Enantiomers.
They're trans to one another. And so because the Diels-Alder is concerted, where are these two groups going to be in relationship to one another? They're going to be trans. Do you guys see that? We didn't discuss this in class. It discusses it in your book a little bit. So I'm sort of using this recitation as to sort of fill in a hole there that I forgot to mention previously. But yeah, that methyl group and that aldehyde are trans to one another. So when the Diels-Alder takes place, they're going to be on opposite sides of one another in the products. Okay? So I'm just going to go ahead and arbitrarily show one as a dash and one as a wedge. Right?
Can it be either?
Yeah. That's why I said I'm arbitrarily choosing one of these, which means that we still have this one stereo center, and that stereo center is the one that we really have to decide between, right? Is it a dash or is it a wedge? And really, those are our two options. And yes, the other enantiomers, but the Diels-Alder reaction, we're not discussing asymmetric Diels-Alder reactions. So every time that we draw an isomer, it could be that isomer or the enantiomer of it. Okay? Yeah.
So that's what I was asking before, like the enantiomer, I don't know, because it can be.
Yeah. These are racemic reactions. They're going to lead to 50-50 mixtures of the enantiomers. We're not discussing asymmetric Diels-Alders here. So as long as you have the right diastereomer, you're good. Okay? But the question becomes now, is that methyl group, because I've already established these, I've just chosen them arbitrarily, but now I'm situated, whether that's a dash or whether that's a wedge, one is going to be endo and one is going to be exo. Now, when I ask Diels-Alder questions, if you look on some of my quizzes and exams in the past, usually it's fairly common that I will say, draw the product with endoselectivity or draw the product with exoselectivity, in large part because I want you guys to be able to draw both, right? And so I may ask you, and I might say draw it exo, or I might say draw it endo. And that's, again, because I don't want you guys just getting in the habit of only drawing one and memorizing how to draw the one. I want you guys to be able to draw both. In general, and it's the case here, that this does follow the endo rule, though, right? The endo is the interesting one. So what I'm going to ask you guys here is, what is the endo product? So if you got up to this point where we were supposed to choose stereochemistry and you weren't sure whether it was endo or exo, it has that pi bond on it, right? And we have a non-aromatic system here. So this will have that secondary orbital interaction that we discussed, leading it to endoselectivity. The question now becomes, great, I know it's endo, how do I draw it one way or another? Yeah.
The methyl on a dash would be an endo product.
Yeah, I haven't thought through the answer yet, so maybe we'll go through it together. So I've already got one vote for dash. Okay, so how would we go about drawing this? Do you remember? You sort of want to show the approach of the endo, right? And so the endo approach is going to be right. We're going to have it flipped around, but we're also going to have it, yes, flipped around and flipped around again, right? Because the aldehyde, I should say in Voltax, because the aldehyde in the endo, right, the aldehyde is the part that's going to be going towards the tail end of the diene, right? That's the part that's going to be participating in that pi-pi stacking interaction in the back, right? And when we're trying to decide the Diels-Alder products, right, I think, personally, if I were to look at this, I wouldn't worry about, so we're going to have a stereo center there, we're going to have a stereo center there, we're going to have a stereo center there. I'm not going to worry about that stereo center right now, because that stereo center is going to be dictated by that stereo center. What I really want to know, because they're closer, and because that's the bond that we're forming, what I think would be really helpful is what's the stereo center here relative to the stereo center there. And that's what I'm going to use to sort of dictate sort of what I'm looking at. And I think to do that, I'm going to show in my protons. Okay, so I draw in my protons at those positions, Christine.
Yeah, you said that our group is moving from towards.
So there's two groups in this case.
Yeah, I was gonna ask you which one. Why?
So the endo. So remember that the endo is dictated by. Okay, so that's a good question, right? Let me just take a step back. The term endo versus exo can sometimes be a little bit arbitrary, right? Because sometimes there can be two groups, and one could be going away and one could be going towards you. There may be some IUPAC prioritization of how to name it. I don't know. But when I think of the endo selectivity, I guess to be a little bit more specific here, Christine, I'm saying endo selective for the aldehyde. And the aldehyde is the one because it has that pi system that's going to interact with the backside pi system here that's going to lead to that selectivity. Does that make sense? Yeah. Okay. But anyways, back to this top side, that's where the stereochemistry I think is a little bit easier to see, right? And again, if you don't want to go through that complex, and I'm sure nobody's going to want to do it at this point because there's easier ways to do it, and I think it's fine because I'm going to do it right now too. How do we decide when these bonds come together, what the orientation, what the relationship between, say, for example, that methyl group and that methyl group are going to be? What's the little visualization that I think makes it easy to see? It's very similar to this visualization, right? These are anti here, and so they're anti here. And so it's helpful on the approach to find the bonds that are going anti to one another. And if you can find those groups that are going sort of anti-periplanar to one another, those will also be the groups that are going anti to one another in the product. Does that make sense? So at this carbon and at this carbon, we're not going to focus on this bond and that bond because those are in the ring. We're really focused on these two versus those two. What are the groups that are anti to one another? Olga, what do you think? What's anti? Well, you should know it if you see it, right? Which are the hydrogen's going this way on this one, and it's going that way on that one. Are those anti? If I were to align those kind of like that, like a Newman projection, would they be anti to one another? Absolutely. So I think for me personally, when I see this, the relationship between that proton and that proton are the visuals that help. You guys all see that? And so in the product, that proton and that proton are going to be on opposite sides. Therefore, this methyl and that methyl are going to be on opposite sides. And so, on the dash. Okay? Is that helpful? Okay, so again, we just spent a lot of time on this one. Okay? We've only got about 20 minutes left to do Cope-Claisen. But this is kind of, I recognize that this is a hard reaction. It's a culmination of all the chemical reactions that we're doing. We've got a reaction where we're pushing a lot of electrons at the same time. We're making a ring. And for some reason, when we make rings, that's often a challenge. We have regioselectivity that's involved with it. And we also have stereochemistry that's involved with it. So it's really a beautiful reaction to, I think, try to tie all these concepts together. And it's for one of these reasons why I really like to emphasize having you guys being able to wrap your head around Diels-Alder chemistry and being able to predict the products of Diels-Alder chemistry. Okay? Okay, and I won't ask you to draw as long as, what I'm going to ask you guys to do is just show the approach being endo, or show the approach being exo, so that I know that you're not just making stuff up. Because I recognize now that I think this is a perfectly fine way to visualize it as well, right? Those are anti, then they should be anti in the product. That also takes some three-dimensional visualization, and if you're artistic and you want to try to draw the transition state, that does become a little bit important when you're thinking about things like maybe more asymmetric chemistry where you may have additional chirality in it, but this covered a lot of topics, so, all right? Okay, so we're prepared for a couple questions like this. In fact, so the way that I asked that question, would you guys like that? If I asked the question and I said, draw the two regioisomers, draw the stereoisomers, I'll just ask for major product.
But you didn't,
I just think it would be easy for me to, I may ask it like this on the exam, because it does help break down different tiers of knowledge.
but you didn't have to draw all the stereoisomers, just the main.
Yeah, it would have been a lot. That's why I'm realizing it. Like, I have to think about how to ask it, but I do like how the way that question was asked,
Yeah.
it built. The problem is if you get the one wrong down here, it does raise questions of double jeopardy, right? If you get this one wrong, can you do that one? That's the one potential problem with that. Right, I'll figure it out. But because I do recognize that there's multiple tiers to understanding Diels-Alder, and I want to make sure that I score everybody accordingly. Christine.
Yeah, when identifying stereochem, do we have to show the protons, or we just
What I was getting at is that the protons, you don't have to show protons. The reason I put the protons there is I think it was a visual aid that helped you. It's same with the chair conformations, right? When we used to do chair conformations, and we'll do some chairs now within them, you're not necessarily, you know, when I teach chair conformations and chair flips and you're focused on the individual carbons, you know, I'm often not telling people put protons everywhere, but it's helpful at least to put the protons at the carbons that you're interested in, because adding those protons can sometimes avoid ambiguity, right? So the only reason I put the 2 protons at those 2 specific carbons were because those were the 2 stereogenic centers that I was interested in. And by drawing them that way, it helped Olga see that they were anti to one another, right? So it provided a visual cue to basically help see what are the groups that are going to be anti to one another. And if you didn't draw them, then it might be a little bit more difficult to do it. So I think, like anything in organic chemistry, it's about drawing molecules oftentimes in a position that helps you see the answer a little bit better. And certainly drawing in protons, not necessarily everywhere, but drawing protons at the positions that can help you see things better is certainly something you should try to do. Does that make sense? Okay. All right, last question. All right, well, I'm certainly going to ask you for transition states of this one. Okay. Okay, so here's one. All right, so another little twist on this question. Okay, so here's a cope. Question is, what's the product of the cope? I want you to pay attention to something, though. Is this chiral?
Yeah, there's a curve.
So what do you think about the product? Is the product going to be chiral? Well, it doesn't necessarily have to be, but the product's going to be chiral. And so I'm sort of adding a little bit of a twist, not twist, but I'm adding a little bit of an extra level to this, which is to say that we have to sort of consider the absolute stereochemistry of this when we consider the absolute stereochemistry of this. I was just talking about the Diels-Alder reaction and how, you know, we're not worrying about, you know, we'll just draw an enantiomer. In this case, there's only going to be a single stereochemical outcome, and it's not okay to have the enantiomers, right? There's only one enantiomer of the product that I want to see. Okay, so let's think about this a little bit. So the first step is, what do we do in this question? So yeah, if I wanted to maybe break this down, maybe we'll do a similar thing. So part 1, draw. You know, maybe the first thing is draw the product. And without worrying necessarily about stereochemistry, right? So to draw it, just making sure that you have all your bond connections right? So maybe that's the C, right? And number 2 is to draw the appropriate stereochemistry, maybe complete with the appropriate enantiomer. So maybe part of this is if you get the right product, stereoisomer, and then maybe an enantiomer. The words I'm using aren't exactly correct, but the point is that maybe if you get the wrong enantiomer, but you get everything else right in terms of stereochemistry, that's maybe the B, and if you get the right enantiomer, that's the A. Or something. I don't know. I'm just trying to sort of illustrate the sort of tiers here. Okay. Okay. So It's 10:30. I'll give you guys maybe we'll just jump to the first one because it's kind of a you know it or you don't know it. So what is the product of the cope?
The same thing.
It's kind of sort of right. It's we have to sort of picture where our electrons are going, right? So I'm not going to discuss stereochemistry here. I'm just going to sort of show where everything is. I'm going to put a squiggle here because we're not saying that it's cis or trans. There's a methyl group. Where's that methyl group?
The allylic to the double bond.
Yeah, sometimes it can help to just draw in the... So it's at carbon 1, right? Right. So the product's going to look something like that. Okay, but we got to give it a little bit more information on it. Yeah.
Shouldn't the methyl also be on either a wedge or a dash because that's also a chiral center?
Yeah. No, I haven't described.
Oh, okay. Just because the other one you put like a squiggle on this one.
Well, squiggle means I haven't both right now are not
Both
defined.
of them aren't, right?
Yeah. So that squiggle is sort of, it could be either,
Okay.
and that squiggle it could be either. I just didn't define it there. It's, you know, it's more difficult to whatever. You got me. All right. Okay. So that's the right isomer. Now the question is, let's draw the appropriate stereoisomer. Now, if I were to say the B grade, for example, I think that, you know, one of the things that should be maybe clear here is, you know, in general, the stereochemistry at the alkene, right? If we're only generating one alkene, what do we know about the cope rearrangement? We were saying at the beginning of class, and Claisen to a certain extent, right? These are reversible, so they're driven by what? Thermodynamic control. So what do you think that alkene stereochemistry is going to want to be? It's going to be trans, right? And we'll have to consider that in the transition state as well, right? So it's going to be trans, and it becomes trans in the pseudo chair by adopting what configuration? Equatorial, right? So the equatorial group on the pseudo chair becomes that. Okay? But now we have a chiral center, so we have to maybe pay a little bit closer attention here. Okay, so if just going to number them, I have no idea if I'm drawing the right chair or not. We'll worry about that once we do it. Okay, so which carbon is the isopropyl group? It's at 4, right? And so at 4, is the isopropyl group going to be pseudoaxial or pseudoequatorial based upon how I draw it? Don't bias yourself to say what ultimately you want it to be. I've drawn it this way. I have to make sure that I stay with the same enantiomer. So at 4, am I axial or equatorial? Axial, right? So it's axial, right? Because I basically taken this group and I put it that way, right? So that isopropyl's coming towards you, it's going to be going up. The group going up at 4 is the isopropyl.
But it's not happening.
But we don't want that, right? Because we just said it's the only group that, you know, that's the group that we could go axial or equatorial. So we got to do this sort of the pseudo chair flip, right? So this is not. I drew it that way. We saw that it's actually not the chair flip. It's not the chair that we want, so we kind of got to do that sort of pseudo chair flip. Now, one of the things to pay attention to here is sort of making an additional point here. Okay, so now, right, this is 1, 2, 3, 4. That's where we wanted to be. Now our 4 is equatorial. Okay. Now, what did you notice about the other pseudo-axial kind of group, or pseudo-equatorial group that we have? Right? I'm just going to make a broader point here. I don't want to confuse people, but I just want to make sure that I emphasize this so you don't get confused. See, we have really 2 groups on this, right? We've got the isopropyl group, which is axial here, and it's equatorial here, right? This methyl group is equatorial, pseudo-equatorial here, right? It's still pseudo-equatorial here. Why can't I change that one? Yeah.
Because it's trans over there, so you're keeping.
Yeah, you're keeping it trans, right? It's trans in both, and this sort of relationship in these, and this sort of analogy in these, is that the trans group is sort of the equatorialish group, right? If I were to draw in a group that was cis here, that would be my axial one, right? So I sort of brought this up last week. I'll restate it, right? That's kind of the cis, but our guy is trans, right? Here, the axial would have been down, right? Because that would have been the cis, but that's not what we have. We have the trans. That make sense? See that? I'm just going to erase those so it's not confusing. Yeah, so perfect. The trans stays trans. Right? So this is the chair conformation that I want you guys to eventually get to, and I want you to be able to draw pseudo chair, and then what we're going to do, right, is we're going to push the electrons around here. Right? And there's our methyl group. Okay? In the product, is it a dash or is it a wedge? Dash. You see that? Right? Because this is sort of going down. And again, Christine, just like before, we were talking about the protons. Sometimes drawing those protons, there's helps. That's another time. You don't have to do it, but drawing that proton, to me, helps a lot. Especially when I'm trying to say, how does this become this? Right? Because really what the product should be is trans. Right? And because this is that, I'm looking basically from the top, which means, and that proton really can help. Right? Because if I'm looking down, I see the proton first. The proton's coming right at me. So I know that the proton's coming towards me, which means the methyl group has to be going away. So it's another instance where drawing that proton in can actually help a lot. Okay? Okay, how are we feeling? A little bit better? A little bit. Okay, so these are the types of questions that you guys are gonna get on the quiz. Okay, so you'll get one on Diels-Alder, and you'll get one on sort of Cope-Claisen. I may try to ask it in a way that can at least help guide us to maybe give partial credit if you don't get it all, but don't plan on that. I'm going to try. You just be able to sort of break it down, and I'll try to figure out the best way to ask the question. But basically at its core, you're going to be given a reaction, you're going to be asked for the products. And you need to know the stereochemical outcome, you need to know the right regiochemical outcome when it comes to Diels-Alder. So, okay, any question? So the antimer would be the exact same thing, just with a dash. Now, if it went through, maybe there's enough time to ask maybe one more question. What would be the product if it went through this? Not that it would. But what is the product that would result from this chair? Let me just give everybody a chance to think about what that would be. Just to sort of to build here and just give everybody a minute to think about that. So this is correct. But had we drawn the product, because that's one of the things that's certainly one of the ways that I may ask questions, right? And this goes back to sort of double jeopardy, right? If I ask you to show me the Cope-Claisen, and I ask you, for example, to show me the chair that leads to that product, right, and then to show the product from that chair. So if I ask you to show the chair of the transition state, and then a product based upon that chair transition state, well, then I'm going to be grading your product based upon the chair that you give me. Does that make sense? I won't be, that's what I'm going to be looking for. I'm going to be looking to see that you can draw a chair and then the product from that chair. The hope is that you draw the right chair and then you draw the right product from that. But if you give me one chair and you have maybe the right product at the end, but it's wrong, then hopefully you guys get what I'm getting at here. It's a two-step process. If you get the first part wrong, you can still get credits for the second part being right. So if you thought that this was the product, what would it look like? Danny?
I have a question about the chair flip that we did.
Yep.
So why is the methyl group still equatorial after we flip?
This and this?
Yeah.
This is what I was saying earlier. It's trans. It has to be trans. You haven't rotated around that. Right? It has to be trans. Right? This is trans. And it just so happens that the parallel is trans and equatorial. Right? But you can't, it's not a true chair flip because it can open up and close back down. So you're not stuck with it, right? And the trans has to stay trans. You're not moving the trans to cis. But anyways, on to this one, right? The product is just going to be the opposite of what we have over there. Oh, I'm sorry. So what you'd want to do is you'd want to one, two, three, four, five, six, right? So if we were to move these, that would go there, that would go there, that would go there, right? This would be 3, 2, 1, 6, 5, 4. Our isopropyl would be there. So this would look like, as it's drawn, the methyl group would still be going towards us. So the methyl group is now going towards us because the proton is going away, right? So as we're looking down, and then our isopropyl group would now be cis. You guys see that? Okay. So again, you made a face. She's getting help there. Bless you. Do you guys see that? Do you understand? So you made a face. Was it clarified? No.
Wait, the methyl group is equatorial on the one?
The methyl group here
Is equatorial.
is still equatorial, right? This goes back to what Danny was saying, right? It's trans, and the trans relates to equatorial, and then I just redrew it in this way. This is not how it's going to go, but this would be the product through this transition state. So for completeness, I thought it would be worth it to just see what the other one would have gone through, because it's going to be important that whatever chair you show the product that's associated with that chair. Does that make sense? Okay. All right. See you guys on Wednesday.